forward. Excuse me. All right, so we've done a bunch of different nucleophilic attacks on carbonyl compounds. As we looked at in the alcohols chapter, we made alcohols by using Grignard reagents, but those aren't the only types of nucleophiles where we can generate a carbon-carbon bond. Okay, so another reaction where we can create a carbon-carbon bond is what we call the cyanohydrin synthesis. And in the cyanohydrin synthesis, what we're doing is we're attacking with the cyano group, which is the C triple bond N. Okay, we're basically making that into a nucleophile by making that a charged species and having that act as the nucleophile and attacking the carbonyl. The good thing about the CN triple bond is that it's a protected carboxylic acid. We can hydrolyze that nitrogen off and get to a carboxylic acid. So you can actually look at it as adding a carboxylic acid indirectly by having this cyanohydrin reaction. Okay, and just like with our other reactions with nucleophiles, because of the partially positive charge on oxygen, our negative charge on our cyanide ion will directly bond to that, giving us our new carbon-carbon sigma bond. Okay, so in this case here, we have our, yes, it's going. We have our electrons from our negative charge on our nucleophile reacting with the carbon of the carbonyl because of that partially positive charge. And then when it does, it forms a charged species here. Okay, so we have a negative charge on oxygen here. So that negative charge is now our base, and so it has to deprotonate something to generate our neutral species here. And notice it regenerates another equivalent of our ion. Okay. So that's the first step in our material, is to have attack by the nucleophile and then a transfer of a proton from the solvent or some other compound. We typically try not to do this reaction, use it with acids, because it is a very acidic solution. So we have some other proton source in the mixture, and we use the deprotonated form as the sodium or the potassium salt. So we'll see this written a lot as the sodium salt or the potassium salt, and then adding an HCl at the end of the system, because we don't want to actually have a whole bunch of this hydrogen cyanide gas, hydrogen cyanide gas. All right, so, come on, there we go. All right, so the reason it's synthetically useful is we can actually get to a bunch of different intermediates that allow us to do reactions. So like I said before, it's a protected carboxylic acid. So what we can do is, instead of having to do something like where we took an alkyl halide and turn it into a Grignard and then react it with CO2, which we'll learn about in the next chapter, we can actually add that carbonyl compound, add that, carboxylic acid group directly to the carbon that had the carbonyl on it. Okay, so in the case of the first step of our cyanohydrin, we react with an acidified potassium cyanide or hydrogen cyanide, and you'll see a lot is, sodium cyanide with HCl. Okay, so that would be like, that's a nitrogen here, sodium cyanide with HCl. And that's the reaction conditions you do to make this cyanohydrin compound here. And then by just adding water to the system, we can actually get it to hydrolyze off the nitrogen and give us the carboxylic acid. And we have what's called a alpha hydroxy acid, meaning that there's a hydroxy, an alcohol group on the carbon next to the carboxylic acid. Okay, and these are used in a lot of biological functions, which is why the cyanohydrin reaction is used for making a lot of pharmaceutical compounds. Okay, so that's one thing we can do. Okay, but we know from our alkenes chapter that we can make double bonds by a dehydration reaction in the presence of a strong acid, a dehydrating acid, one that removes water. So in the case of if we instead using HCl with a lot of water here, use just sulfuric acid as our dehydrating acid, so it's going to remove water, it's still going to hydrolyze off the nitrogen group. But what it's going to do is it's going to take away this water and the hydrogen over here to generate a double bond. And this double bond is in conjugation with the carbonyl of the carboxylic acid. So let me redraw this to show you that it's in conjugation here. So this is just redrawing this structure here, showing you that now our double bond here is in conjugation with our carbonyl of our carboxylic acid. And that makes it particularly stable. And then we can go on and do additional reactions on this unsaturated carboxylic acid. We can make other derivatives of it. Okay. But that's not the only thing we can do, okay? So we've hydrolyzed the cyano group down to a carboxylic acid, and then we can either make it an unsaturated system or have that hydroxy acid. The other thing we can do with it is we can actually take that cyanide compound and add hydrogen across it, okay? Because that cyano compound is like a carbonyl compound in the fact it's got a carbon double bonded to a heteroatom, like oxygen, and in this case, nitrogen. We can actually start adding hydrogens across there. Once we add enough hydrogens across there, we'll end up with a primary amine. So this is just adding a total of 4 hydrogens to that carbon-nitrogen triple bond to give us our primary amine. Okay, and this has a really neat structure because we have an alcohol functionality 1 carbon over from an amine functionality. And so we call those beta amino alcohols. Okay. So these are also have a lot of uses we can do in biological systems because you can add things across both of these and make big rings. Okay, so we can hydrolyze our cyano group there. We can reduce down our cyano group there. We can eliminate our hydroxy group to give us conjugation. Okay. So the next reaction I want to talk about is let's take that carbonyl compound and turn it into a carbon-carbon bond, but not just a single bond. In this case, we made a carbon-carbon single bond where that carbonyl carbon was. Instead, let's use a different set of reagents so we can selectively put a carbon-carbon double bond right where that carbonyl is, okay? And this is called the Wittig reaction, okay? It's German, it's pronounced Wittig, but it's spelled Wittig, so. Okay, so in the Wittig reaction, what we have is we have a phosphorus compound, and phosphorus is one of these things that we call oxophilic, okay? If a phosphorus can react to form a phosphorus oxygen bond, it will. Now, if you remember back to our alcohols chapter, when we converted alcohols to alkyl halides, we could do that with phosphorus pentachloride, and the byproduct was a phosphorus oxygen bond. We have that same type of reaction, the driving force getting us to these carbon-carbon double bonds, okay? But the reagents look a little different. So looking at our reagents here, we can use an aldehyde or a ketone as our starting material, as long as you have that carbonyl that is not an ester. That's a different reaction. You can use it to create this carbon-carbon double bond. And the way we do that is we create an initial compound, an initial complex with the phosphorus such that we now have a carbon anion, okay? We've used carbon anions before in things like the organolithium reagents and in the Grignard reagents here. But this particular one has a phosphorus carbon bond stabilizing the negative charge on the carbon, making it very selective about where it goes. But just like with the reaction between the Grignard reagent or an alkyl halide, it's going to attack the carbonyl carbon because of its partially positive charge. Okay. Now, the net result of this reaction is we're going to end up eliminating the oxygen and the phosphorus to give us a carbon-carbon double bond and our new phosphorus oxygen double bond. Okay. Now, these will create E or Z isomers. If you're only disubstituted, that creates cis and trans isomers. Okay. So let's do a couple of examples. You can use very simple compounds, like if you had a uh, iodomethane and you reacted it with phosphorus, you could generate a very small compound like this right here. And this is the actual reactive species, and I'll show you how to create this in solution. Okay. Then in this case, we're reacting it with this very simple aldehyde. This is acid aldehyde. And so it only has the one methyl group here, and we're going to be adding just one carbon to it. So we've extended the molecule by one carbon, and we know exactly where that double bond is going to be. That double bond is going to be exactly where the carbonyl carbon was. Okay. And then, of course, our phosphorus oxide byproducts. In the case of this cyclic ketone here, we're going to add, instead of just one carbon, we're going to add two carbons here, which is going to give us an E or Z isomer here. And so we've, again, added the double bond exactly where the carbonyl was, but we've extended the chain by two carbons. Okay. So unlike things when we dehydrate alcohols where you have carbocation rearrangements and you have to follow Zaitsev's rule where the more substituted double bond is more stable, you eliminate those rearrangements and that requirement using the Wittig reaction. These are very good at making terminal alkenes. Okay, so that's where we want to use this reaction specifically. If you don't want that carbon-carbon bond to move around, we want to use the Wittig reaction. Okay, so let's move on to how we actually do the reaction. Okay, so the first thing we have to do is we have to generate that actual reactive species, that carbon phosphorus bond. And most of the time when we do this, we use what we call triphenyl phosphine. Okay, so that's just a phosphorus with three phenyl groups on it. Okay, and then we react that to generate this reactive species here. And notice there is no net charge because there's a positive charge on phosphorus and a negative charge on carbon. So really, if we look at a resonance contributor, we end up with this structure here, which is a neutral species. Okay. And yes, if you count the electrons around it, you do have 10 electrons around phosphorus. But remember, phosphorus is one row down from carbon and has available orbitals. Remember, phosphorus and sulfur can bond up to 5 times in our reactions here. So that's one of the special things. Okay. So when we create this phosphorus carbon species right here, this is what we call an ylide. Okay. And an ylide is specifically a compound with two oppositely charged atoms bonded together. And when they are in their when they're in their charged state, each atom has an octet. However, we can draw a resonance structure so that each atom has no charge, but one of them has more than the octet. Okay, so that's the kind of the definition or sticky wicket of the ylide is it technically has this double charge species. However, by resonance, it actually has no charge. Okay, so how do we make it? So we make it in a couple different steps. The first step is we start with an alkyl halide. Okay, so it can be a methyl alkyl halide, a primary alkyl halide, or a secondary alkyl halide. But you cannot use a tertiary alkyl halide because you have to have a hydrogen on the carbon you're going to bond the phosphorus to. And I'll show you why. Okay, so the first step of our reaction is that our phosphorus right here has a lone pair on it, and it acts as a nucleophile to displace a leaving group. Most of the time, it's a halogen, like a bromine or an iodide. Okay, so when we displace that halogen, we create our first step in the system right here, which is our charged complex with a positive charge on phosphorus, and our halide is that counterbalancing charge. Okay, so this in itself is not nucleophilic. The carbon does not have a negative charge yet. So what we do is to make the carbon have a negative charge is we pull off the hydrogen that's bonded to that carbon with a base. Okay, now notice that has to be a pretty strong base. okay, because that's not a very acidic hydrogen, right? The carbon bonded to hydrogen, that's a very non-acidic bond. But when we use a strong base like um, these lithium reagents, like butyl lithium or alkyl lithiums right here, we can pull that hydrogen off. And this goes off as butane, because now it's a nice neutral species, and drives the reaction to form our active species, this phosphorus ylide. Okay, notice that by resonance, it'll have a double bond in between here, but we have a negative charge residing on the carbon. Our carbon is now our nucleophile. Okay, so an example of how that would look in a reaction would be like here, where we'd have this triphenyl phosphine right here. Notice there's only 3 bonds to phosphorus at the time, and so it has a lone pair. It's going to react as a nucleophile with an alkyl halide to generate our intermediate species here. And then we're going to react that charged species with any kind of organolithium reagent. In this case, we're actually using phenolithium. And we will generate our active anion, carbon anion, plus a neutral material. And in this case, because it transfers a proton from this methyl group to the phenyl group, we get our neutral benzene as our byproduct and a salt. Okay, so this is all just to form our nucleophile. Now that we have our nucleophile, we can react it with our species. That's the next step. Questions on formation of the ylide. Okay, so the key feature is we have a negative charge on carbon. Those electrons are going to create our new sigma bond. Okay, just like in a Grignard reaction. So now we formed this negative charge, and now our negative charge on carbon is going to act as our nucleophile and attack the carbon of the carbonyl. Okay. Now, in this case, what happens is instead of doing it'll go through that tetrahedral intermediate here, and we're going to form this compound here where the electrons end up on this oxygen here, but we have a positive charge on the sulfur, on the phosphorus right next to it. So what's going to happen is that negative charge that forms on oxygen is going to form a new sigma bond between the oxygen and the phosphorus, and the electrons from the ylide, from the carbon, are going to form a new sigma bond with the carbonyl carbon. Okay, so it's going to form this ring structure, and we call that an oxaphosphatane, okay, because it's got 4 members in a ring, it's got 2 carbons, and oxygen and phosphorus. Okay, what's going to happen now is because the oxygen phosphorus bond is so strong, what's going to happen is it would like to eliminate that phosphorus oxygen out of that strained ring. And when we do that, we have the electrons from the phosphorus kick in to form our pi bond. The electrons from our carbon-oxygen bond here are going to form our double bond between oxygen and phosphorus. Notice there are 10 electrons around phosphorus now. Okay, but the key feature here is we've now formed a new carbon-carbon double bond. Okay, the initial anion forms our sigma bond. The elimination of the phosphorus and oxygen formed our pi bond. Okay, so what that kind of looks like stepwise is you could have your nice example of a ketone here. And in this case, the 3 phenyl rings on phosphorus are not transferred. Only the alkyl group that is on the other side of the phosphorus is transferred. And in this case, it's a CH2. So when we go through our intermediate here, we'll know exactly where that carbon's going to end up. And we adding exactly a CH2 to the carbon where the carbonyl was. Okay. So notice this is outside the ring, right? Zaitsev's rule says if we were going to form that double bond by a dehydration, it would want to be in the ring. We would want to be more substituted. Okay, so this is one of the few reactions we have that makes the least substituted alkene. Okay, questions on that? All right, we got about 20 minutes left. We're going to get completely through this and a derivative. And maybe I'll introduce carboxylic acids as well. Okay, so when we think about this, we want to look at how it's synthetically useful. And I said this is one of the few ways to make that least substituted alkene. So when you're looking at compounds that have these really weird unsubstituted alkenes, start thinking, ooh, I think we went through an I think we went through a Wittig reaction. And whenever we have that, we have to break it down into what had the alkyl halide and what had the aldehyde or ketone. Okay, so if it, so let's break that down and try to figure out which direction it's going to be. Okay, so in the case of this compound here, okay, we only have one double bond, so we know that's where the Wittig reaction happened. Okay, and so we can break it into two different ways. Okay, so we could have it where if one side is the alkyl halide, the other side has to be the ketone or aldehyde. Okay, it has to have the carbonyl compound. So we can break it two different ways, right? So if we just look at this compound and say, okay, let's break this both ways and see which one is going to be something we have. So if we have this compound and we're breaking it here, and let's say this side right here, if we had that as an alkyl halide, it would be something like this right here, which means the other side has to be the ketone, which would make it a carbonyl compound. It's an aldehyde because there's a hydrogen here and a methyl group here. Okay, so if we were going to have the carbonyl compound on this shorter chain, this side chain, it must be an aldehyde because of the presence of this hydrogen here. Okay, so that's one possible reaction mixture we could have on that, because we're having the carbonyl has to be on one of those two double bonded. The other way we can break it up is to, instead of doing that, what if we had the alkyl halide on the other side? To have the alkyl halide on the other side, so that would have to be, this one is the alkyl halide, so that would have to be a CH2CH3 with a bromine on it, but that means the other side has to be the ketone. So we have to have our ketone on the other side. Now, it doesn't matter which way you build it, as long as you can form the alkyl, as long as you have an alkyl halide and a matching ketone, you can do it by either direction. Notice in this case, we have a ketone and a primary alkyl halide. In the other situation, we had an aldehyde and a secondary alkyl halide. Okay. So again, it all depends on which reagents you have available to you to see which way the Wittig reaction will go. So, so let's show you the two different possibilities here of what we can do. So if we form the ylide with our alkyl halide of the alkyl group here, that means when we backed up, it would give us that primary alkyl halide. And if we had the ylide forming on this cyclopentyl group here, that means we had to have that secondary alkyl halide here. And again, the ketone or aldehyde depends on which one you formed the alkyl halide from. All right, questions on that? So the key here is to look for where the double bond is and know that one of those substrates had to have a carbonyl and one of them had to have a halide. And then just being able to choose which one is, but they'll both work. You just have to look at your starting materials. Okay. So the number one advantage of the Wittig reaction is because you do not go through a carbocation intermediate like you do in an E1 elimination, you can choose exactly where you want it to be. It does not rearrange, okay? So for example, if we were to do a reaction where we dehydrate a tertiary alcohol, we're gonna get our more substituted product as our major product. However, the VIDIG will say the double bond's always going to be where the ketone is or the aldehyde was, and therefore you only get one product. You don't get a mixture of products. Okay. So there is a derivative of the VIDIG reaction where instead of using triphenyl phosphine, you actually use a phosphine ester. And whoa, that's not what I wanted to do. It's down here. There it is. Okay, so instead of using that triphenyl phosphine, we can use this triethyl phosphite. Okay, the advantage is the triethyl phosphate's a little more, a little less toxic, and so sometimes it can be used, but it does the exact same thing. It generates a phosphorus carbon bond. You use a base to create your carbon anion right here. And once you create that carbon anion, it reacts exactly in the same mechanism as the VIDIG does and will give you an alkene. Okay. The difference is because of the variation here, it predominantly produces cis or E alkenes, where the VIDIG makes a mixture of E and Z. The phosphate ester derivative of it predominantly makes the trans or E derivatives. And again, it's the same mechanism. We're forming the same kind of phosphine oxide bond, and we're forming a double bond from the system. All right. Okay, the last thing I want to talk about is that we have available to us the idea ketones really don't oxidize, okay? They are pretty darn stable. We can eventually oxidize them down if they have available hydrogens to carboxylic acids. However, aldehydes are also much more easily oxidized in the system. And so we don't have to go with a strong oxidizing agent like permanganate or a chromium to get an aldehyde to oxidize all the way down to a carboxylic acid. We can actually use a much softer reagent. And in this case, we're going to use what we call these silver reagents, or where they are going from silver +1 to silver 0. And as they do that, they're stealing an electron away from the system and oxidizing down your carbon. And most of these are done in the presence of water or base, and therefore your oxygen is transferred from the water or the base. Okay, so aldehydes will actually oxidize just slowly in air, and so sometimes you have to protect them. However, you can also use either the silver oxide reagent right here. And again, it's transferring an electron from this carbon here. We're changing its oxidation state. And it's transferring the electron to the silver here and giving us our alkoxide. Notice this is in base, so we generate an alkoxide and we have to acidify at the end of the reaction. We also have another reagent for us, but it does exactly the same thing. It transfers an electron from the carbon of the aldehyde to the silver to generate a silver 0 compound. And when it does this, it plates out as metallic silver on the system. And this is occasionally used as a qualitative test to tell the difference between aldehydes and ketones, okay? Ketones won't react with this system, okay, because it's such a soft oxidizer. So you can add this basic silver ammonium compound to a ketone and nothing will happen. It'll just stay in a murky solution. However, if you do it in the presence of an aldehyde, it will transfer that, it'll oxidize off that hydrogen and generate a metallic silver sheen. And so when you do it in a test tube, it'll actually look like a mirror. And it's called the silver mirror test or the Tollens test. Okay, so that's just one of those unusual reactions that only aldehydes do, and it's used to differentiate aldehydes and ketones. All right, questions on that? With our last 10 minutes, I want to do a reaction wheel to show you when we would use different things like the acetal versus the thioacetal versus the other reducing agents, okay? So I'm gonna stop sharing that and pull up this one right here, okay? So the net sum game of any of these reactions we're talking about is selectivity, okay? We want to be selective on the reagent we choose, and we want to react on just one reaction site. So how can we kind of drive that to, with just some of the reactions we looked at today? So what I want to do is I want to take this reagent right here. This is our starting material. And I want to do a couple things to it to show you we can generate different species. Actually, let me not draw that as that. Let me draw it as this. All right. So in this case here, we have a ketone and we have an ester. Okay. And so if we just took a reducing agent like sodium borohydride, right here, the sodium borohydride would not reduce down the ester. It would only reduce down the ketone, yielding a secondary alcohol over here. And our ester would remain untouched. Okay, so that's great. If we wanted to have our ester and our secondary alcohol, we could just use sodium borohydride. But what if you made a mistake and you accidentally used lithium aluminum hydride instead? What would happen? Okay, we would have a different product because lithium aluminum hydride does reduce down the ester as well. Okay, so that would give you a different product. Lithium aluminum hydride, or LAH, would give us our secondary alcohol, and it would reduce our ester down to a primary alcohol. So now we'd have this cyclic structure with a primary alcohol and a secondary alcohol, which is great if that's what you wanted, if you wanted to diol species. Okay, what if you wanted a primary alcohol, but you wanted to keep your ketone? Okay, if you wanted an alcohol and you wanted to keep that ketone, you would have to change the reaction you used. You'd have to protect your carbonyl compound. And the way we do that would be we would protect our carbonyl compound with the acetal. We would, and I usually use the cyclic one, so we'd use that with tosic acid here. And so the first step would be protecting our carbonyl compound, and it would give us this nice little five-membered ring with 2 oxygens in it. We'd have our ester here, still there. And then if we reacted that with lithium aluminum hydride, and then we clipped off that acetal in 2 steps, one would be lithium aluminum hydride, and then followed by acid, step 1, step 2, we would generate our carbonyl compound back again and our primary alcohol. Okay. So that's cool. We have selectivity in our reagents. We can react just the aldehyde. Just the ester. We can react both the ester and the carbonyl. We can react just the ketone. What if we actually wanted just a single primary alcohol? We'd have to use one of those other reagents. We'd have to use a thioacetal. Okay, so if we did our thioacetal, where we had our SH like this right here, it would generate our intermediate species, which would be that thioacetal. Those are S's right here, and we'd still have our ester here. We could then react that ester with lithium aluminum hydride, and at the end of the reaction, we would hit it with rainy nickel. And if we hit that lithium aluminum hydride and rainy nickel, that would reduce this off and turn it into a CH2. And we'd end up with a completely different product. We have a cyclohexane with a primary alcohol hanging off Okay, so this is what when you start studying this and looking at why would I use a different reagent, this kind of reaction wheel shows you that using the same starting material and changing the order of the reagents you used, we've actually generated 1, 2, 3, 4, 5 different products. Okay, so when you think about reactions, think about selectivity. When you think about protecting carbonyls, think about acetals and thioacetals. Or you can even do that with amines. Imines, I-M-I-N, imines. All right, questions on chapter 16? Is anybody out there? I must say you've been exceptionally quiet today. Okay, I'm gonna stop recording and this will be all up there. And I'll post this as soon as